Okay, in this unit, we're going to start working on actually building deep networks. Deep networks are built with frameworks. A framework can be viewed as a high-level language in which you write your model and which automates the construction of the stochastic gradient descent training algorithms. So let's think about what a model is. A model is some way of taking a setting of the model's parameters and defining typically a probability of a label for a given input. More generally, a model is some way of mapping a particular setting of its parameter values and a particular input to a loss. Like in the fundamental equation of deep learning, the loss is the negative log probability of the label given the input. But in general, any way of mapping a training point, like an XY pair, and a parameter setting to a loss is something that a framework can implement and is a deep learning network. Frameworks typically also provide support for managing large training sets and for managing particular settings of the parameters, particular models, particular parameter values. So it involves a variety of support for deep learning. There are many frameworks that have been built over the years since the deep revolution. Today, the two dominant frameworks are PyTorch and TensorFlow. TensorFlow is generally used within Google and on Google's tensor processing unit, TPUs. PyTorch is popular at Facebook and a lot of people, I think PyTorch is probably among academics, the preferable framework at the moment. In this class, we have what we call the educational framework, EDF. EDF is 150 lines of NumPy Python code, very small, a couple pages. It's a fully functional framework, and it's intended to let students see all the nitty-gritty details, just straight up from NumPy Python. Okay, so in the first problem set for this course, we're going to be doing MNIST digit classification. So I'm going to use that as an example of what a framework can provide. And the problem set is going to have this done in the EDF framework. So the MNIST digit recognition example is what is considered these days to be a kind of toy example. We have images of digits viewed as vectors as inputs, and we're going to try to classify an image as one of the 9 digits, one of the 10 digits, 0 through 9, using a multi-layer perceptron, or MLP. So this is an example of multi-class classification. We assume some population distribution on pairs of inputs and labels. We have 10 labels. The input is a 28 by 28 image, which we're going to think of as a 784 dimensional vector. So we just think of the input as a big vector in a high dimensional space. And we have a training set, which is a bunch of these XY pairs. X is the input, Y is the label. Okay, we're going to try to classify these digits, these images of digits, using a multi-layer perceptron. So a multi-layer perceptron takes the input X, and it first computes a hidden layer. The hidden layer is a vector. You can think of it as representing some features for the input. The way this works is the input is a vector. We apply a matrix to that vector. Each component of the result is a different linear combination of these input vectors. Then we've got a bias vector. So for each component of this vector, there's a bias term that we compare to. And you can think of that as the threshold that we're expecting this linear combination to reach. And if this linear combination reaches that threshold, then this difference is greater than 0. And we take each component of this vector and we pass it through, I'm tempted to call this a threshold function, but it's in deep learning, it's called an activation function. So this is going to compare the components of this vector to 0, and it's going to activate, give it a strong positive value when this vector component is large compared to 0. So this is a hidden layer. This is a set of, you can think of each component here as the output of one linear threshold unit. Each component here is the result of a linear combination of X values compared to a threshold and passed through an activation function, kind of linear threshold unit. Now we just do it again. Okay, when we do it again, this matrix is going to take something that's potentially a high dimensional vector. The dimension of this vector could be larger or smaller than the dimension of X. But we're going to take whatever the dimension is of that hidden vector, and we're going to, through this matrix, we're going to push that down to a 10-dimensional score vector. So now we do the same thing. We compute 10 dimensions for each output component. We compare it to a threshold, pass it through an activation function, but this time we're getting a score. And finally, we do a softmax over the possible labels, the digits 0 through 9. We do a softmax operation to convert these scores into a probability distribution over the labels, which we can then apply the log loss cross entropy loss function. All right, I want to just say a few words about activation functions. These are like the thresholds in a linear threshold unit. Sort of the original fundamental activation function is the sigmoid. So this function starts, it's 0 for when the value is negative. When the value reaches the threshold 0, it increases and then plateaus at 1. And if you look at this formula, we talked about softmax in the binary case. This is just the binary case softmax function. So this is graphing the probability of y given m for a margin m. Anyway, it's the sigmoid function. It's a smooth transition from 0 to 1. So it's sort of like a threshold. Other common activation functions, there's the rectified linear unit, or ReLU. The ReLU is 0 until it's activated, until it reaches the threshold, and then it's linear. It just becomes the value of the margin beyond that. And there are good reasons that the ReLU is often, if not usually, preferable to the sigmoid. And we'll talk about that later in the course. And then another common activation function is tanh. Tanh is basically the same as sigmoid, except that it's transformed to go from -1 to 1 rather than 0 to 1. And this is typically used in gates. And we'll talk about that when we do RNNs later in the class. Okay, so the framework is a compiler for high-level source code. How do we think of high-level source code? In this class, I'm going to think of it as a sequence of assignments. So the source code is this sequence of assignments. It assigns a value to this hidden layer, and then to the scores. Then it converts the scores to probability, and then there's a loss function. If you read other textbooks or other treatments of this material, they'll talk about a computational graph. I strongly prefer to think of this as source code rather than a graph. But just to point out the graph interpretation, you can think of each variable in the source code that's being assigned as a node in a graph, and each assignment statement as a kind of edge or hyper edge relating this node to other variables in the program, other nodes in the graph. So there is a graph theoretic way of describing the high-level code that the framework compiles. But in the EDF implementation, it's much more natural and perspicuous to treat this as a linear sequence of assignment statements. So what the framework is going to do for us is automatically compute the gradient of the loss with respect to the parameters of the network. So in stochastic gradient descent, we're going to want to update the parameter values so as to improve or reduce the loss. And the framework is going to automate that. All you have to do when using a framework is to write the model. So here's just the definition of stochastic gradient descent. So we're trying to minimize this loss. We're trying to set the model parameters so as to minimize the loss. Typically in stochastic gradient descent, we use some random initialization of the network parameters. And then we enter this loop where we repeat until we converge. We're going to draw a point from the training data. If you want to be theoretically clean, you can draw that at random from the training data. In implementations, you typically walk through the training data one point at a time. But you take a training instance, so Z here could be an XY pair. Then you compute the gradient of your loss function. For each parameter, you're computing the derivative of the loss with respect to that parameter. That's this gradient vector. It has a number for each parameter, a derivative for each parameter. And then you update your model parameters so as to improve the loss. And there's this eta, which is the learning rate, which controls the size of the update. Typically, you want that update to be quite small for one training point. You'll also hear the phrase epoch. So an epoch is one pass through the training data. So in practice, you walk through the training data one point at a time. For each point in the training data, you update your model parameters. And when you'll often see what's called a learning curve, which is the loss as a function of the number of epochs of training. So when I first encountered deep learning recently, sort of got involved in the literature, I had to ask somebody, what was an epoch? So the summary, what is a framework? A framework is a high-level language for defining models that automates stochastic gradient descent and provides a lot of other support for data structures and file storage and so on. Okay, so we're going to continue in the next unit talking about backpropagation and how exactly the frameworks implement that. Thank you.